Hi, welcome to another video on Know the Basics of Circuits series. So in this video, we will see how to use SPICE simulation tool to analyze the frequency response of a given circuit. So now we mainly concentrate on frequency response of a circuit using Ltspice. Okay, these are the prerequisites. Okay, with this initial thoughts of so let us start with uh, now we are looking at frequency response of a circuit. Since we are talking about frequency response of circuit, so let us consider a circuit whose response changes with the frequency of the input signal. So let me consider this RC network. This is R, this is C. Let this C be 1 microfarad, let this R be 1 kilo ohm, and let me have this as a input signal, and let me measure this as the output. Of course, this is the ground. Now since I want to find the frequency response of this circuit, so this input signal Vin, which we'll be considering a sine wave, we should not be specifying the frequency of this, meaning, so this should not be a single frequency of maybe 1 kilohertz. It cannot be a single frequency. Now I need to specify the range of frequency over which it changes. So range of frequency means it can be from 10 hertz to maybe 100 kilohertz, or it can be 1 megahertz, something like that. So I have to specify the frequency range over which I have to measure the output of this, meaning the graph what we are looking at is on x-axis I am going to have the frequency, on y-axis it can be the output voltage, or it can be output by input, which happens to be the gain of the system. Usually frequency responses, since it is frequency, you are varying it from maybe 10 hertz to 100 kilohertz or 1 megahertz, even maybe larger frequencies. Now this scale, the horizontal scale is in log scale. So it in log scale, meaning that this is 10, next it is 100, you'll have it as 1k. Of course, this is logarithmic variation. This is logarithmic variation. Then this is 10k, then this is 100k. This is how you can able to accommodate very high frequency signals on this scale of logarithmic, and this will be usually in dBs, meaning it will be 20 log of this quantity. V naught by V in will be the magnitude that will be plotted on y-axis. So this is in dBs. So typically in most of the cases this will be in logarithmic, this will be in dBs whenever you are plotting the frequency response of a system. Now let us try to use Ltspice and try to see how do we do all these frequency response of a very simple RC circuit. So let me go to this Ltspice. Okay, this is, let me take a new draft. Let me name it as let me name this as, it's always better to name the circuit. So name the circuit file. This is RC network, RC network with frequency response. Maybe let us put it as one. So now let me close this. Okay. let me have a resistor, control R here, and then I want to have a capacitor here, and then I need to have a voltage source. You have a voltage source here. Sorry, let me have a ground also. It is G now. Now you can start wiring it. Type W. You can start from here, go all the way, just run through the components to make the connection. I'm just running through. This is my circuit and this is ground, and I will change this value to 1k and this value to 1 microfarad. 1u corresponds to microfarad. You can see by default it is coming as also. And let me say this as v naught. V output is here, and let me change this to v input. This is the input. See, this is v input, this is v output. But in my trace, I can see the name of this as input as input and output as v out. And as I said, uh, we need to set this source as, this should not be a sine source. Suppose if it is a sine source, I have to specify the frequency. So this should not be a sine source. Whenever, okay, just note this very carefully, whenever you are doing frequency response of a given circuit, the function should be, just go to this none and give the AC amplitude as 1. So this is none, functions is none, and AC amplitude is 1. Then you can say you are there. Can you see this is a AC amplitude of 1? So this is the V in source. So this is like, so as I just said here, I'm not supposed to make this frequency as 1k. This is not allowed. So I'm simply applying a sine wave of 1 magnitude 1. This is also not even called as 1 volt. It is a magnitude of 1. And you may be wondering, where do I specify this frequency range? So that is specified in the analysis here. So this is in the configure analysis. In the analysis configuration, I will be selecting AC analysis. Please note, I have to do a AC analysis for doing frequency response. This is AC analysis, and it will ask for what type of sweep. So type of sweep is actually decade. Why it is decade means it is due to this reason. Can you see this is in happening in logarithmic, and this is like decade. This is 10, 100, 1k, 10k, 100k. So this is varying in decades. So that's why the sweep type should be decade. Got it? And then how many points per decade you want to plot. So let us have more number of points so that your graph looks smooth. So this is your number of points per decade. So in one decade you're going to have 10 simulation results, so that the graph, when you plot the graph looks very smooth. And start frequency, as we said, so let this be 10, and the end frequency, stop frequency, let it be 100. Now this is the simulation setup. The configuration of this circuit is now set to frequency response, which is nothing but dot AC. It's a decade type of sweep. Number of points per decade is 100. 10 is the starting frequency, 10 hertz, and 100 kilohertz is the stop frequency. So we are ready to do the frequency response. Now I can do run. You can see now the moment I run, you can see now this is starting from 10 hertz to 100 kilohertz. Can you see the scale here? Can you see the scale is now, it is keep this is actually what is called as a logarithmic variation. This is in log scale. Then what you're supposed to plot here, I'm supposed to plot this V naught, because I'm interested in what is V naught in frequency response. When I plot this V naught, can you see this is my V naught? This is V of V output. So whatever that you are getting now here is V of output. Since okay, just give me 1 minute for clarification. So what is the input that we have taken? We have taken the input as 1. We have taken the input as 1. So what is the output you are plotting? You are plotting V of VOP. This is what you're plotting. What is the input? Input is actually 1. So input is 1. So what is the ratio of this V out by V in now? V of V in. Is it not V of VOP by 1? Is it not V of VOP only? Meaning whatever you plot, since this magnitude is 1, if you are plotting this, so this itself will be V naught by V in. So even though you are not plotting V naught by V in, since V in is 1, V naught itself is the gain of the circuit in dBs. So that's why if you can see here, whatever response that you're getting now is the output response, also the gain of the circuit, because input is 1. When it's very simple that if you have something X here, if you are having maybe some X volts, if the input is 1, then what is V naught is? V naught is X volt. What is V in? V in is 1 volt. So what is V naught by V in? V naught by V in is the gain of the circuit. Gain of the circuit is nothing but V naught by 1, which is equal to V naught itself. So gain of the circuit is V naught itself. So that's why we will going to keep the amplitude of your input as 1 volt, so that even if I measure the output voltage, this represents the gain of the circuit. Now to just make sure that output itself is the gain of the circuit, so we make input as amplitude of 1. Correct? So now you can carefully notice something here. On x-axis it is the frequency. Can you see this is 10 hertz, 100, 1k, 10k, 100k. This is as per our setup. On the y-axis, on the left hand side, you can see this is in dBs. So this is maximum is 0, then it is -6, -12, it is keep going like this. And you can see on the right hand side of the y-axis you have these in degrees. This is 0 degree, 9 degree, 8 minus 18 degree, minus 27 degrees. Of course, can you see these are all in degrees? So you will be wondering, okay, why you have this in dBs and why this is in degrees. And you can carefully notice that there are two plots. One is this plot, other is this dotted one. So this is actually the magnitude plot. This is the phase plot of the circuit. So now let us try to understand what is this magnitude plot and phase plot, why that comes whenever you're doing a frequency response of a circuit. So now let us take up this circuit and try to find out why we are getting two plots. One I said it as magnitude plot, and other is phase plot. So let us try to understand why you are getting two plots and what is the significance of that. So this is V naught, this is R, this is C, this is plus minus. Now I know that this is I, this is V in, this is V naught. So what is V naught is equal to, shall I say this is I multiplied by, suppose if I say this is some impedance ZC. This is the impedance of, because this is a reactive component, let me say it has got some impedance of X ZC. So I know that this ZC is nothing but 1 over JXC. 1 over JXC. So I can write it as I into 1 over JXC. But what is this I? What I want actually is, I want to know what is V naught by V. I want to know what is V naught by V. So this is I into 1 over JXC. So what is this I? So I is nothing but the current flowing through this. I can write the I as equal to V in divided by the entire impedance. So what are the impedance? It is R plus ZC, which is nothing but V in by R plus 1 over JXC. Correct? I can write this. Now, upon writing this, So let me substitute what is I here. So can I write it as V in by R plus 1 over jxc into 1 over jxc. So now what will happen here? So now I can write it as okay, what is, by the way, what is xc? It is 2 pi fc, or xc is equal to omega c, where omega is 2 pi f. So where c is the capacitance of this capacitor. So this is what is xc is, it is omega c, which is nothing but, omega is nothing but angular frequency, it is 2 pi f into c. So now let me just find out, this is v naught is equal to v in. So this is what you have is, uh, let me take the LCM here. It is R jxc plus 1 by jxc, and this is into 1 over jxc. So let me just again slightly simplify this. V in by jxc by 1 plus jrxc into 1 over jxc. Does these two go off? These two go off, then you end up with, this is actually V naught. This is actually V naught. So now if I take this V in here, can I write V naught by V in as equal to 1 over 1 plus jrxc. I can write like this. So what is this xc? Xc is nothing but 1 over 1 plus j r 2 pi fc, 2 pi fc. So now this is a complex quantity. So now we are having something like 1 plus jb. 1 plus jb is your complex quantity, which is v naught by vn. So now since it is complex in nature, this is going to have some magnitude and phase. So what is the magnitude of this? It is 1 over under root of a square plus b square, and phase is tan inverse of b by a. Correct? The magnitude is 1 over so and so, and phase is, of course, it is in the denominator, tan inverse of b by a. So now if I take the phase onto numerator, does v naught by v in is the magnitude is 1 over a square plus b square, is the phase is minus tan inverse of what is b? B in place, of course, let me write it as b by a. So what is in place of a? You have, in place of a you have 1, because a is nothing but coefficient of real term. This is coefficient of imaginary, which is b is r omega c. R omega c, r nothing but r 2 pi fc. Correct? So I will write this as 1 over root of 1 square plus r 2 pi fc whole square minus tan inverse of what is b? B is this, tan inverse of 2 pi r fc. So v naught by v in is having a magnitude of 1 over 1 plus r 2 pi fc whole square. If you want to get this in dBs, it is 20 log of this quantity. 1 over the root of, this is square, 1 plus 2r pi fc whole square. Since it is a denominator, you can take it to numerator, then this will become minus 20 log of under root of 1 plus 2 pi r fc whole square. Now what is the parameter that is keep on changing? F is a parameter that is keep on changing. So you keep the value of f changing from 10, 20, 100, 500, 700 or whatever value, 1k, 10k, 25k, 60k, 80k, 100k. Keep on giving different values of omega for a value of r is equal to 1k and c is equal to 1 microfarad. You will get different gain magnitude. So that's what is this. That's what is this. This is what frequency. What is this? This is V naught by V in dBs. See here, that's what you're getting here. That's what is this magnitude. That's what is this magnitude. And how about this phase? That phase is nothing but this. So what is phase here? Phase is this. So phase is minus tan inverse of 2 pi RFC. Here also R is known, C is known. Keep on giving different values of F. That is, what are these different values of F? You will get different phase. So you will get a phase which is keep going like this. So this is your phase which is going like this. So this is magnitude plot, this is phase plot. So that's why whenever you do frequency response, we will always have two plots. One is with, of course, both of them are with respect to frequency. One is magnitude in dBs and the other values will be specified in terms of degrees. So what is the phase at a given frequency? What is the phase? So what you can do is, so you can do one thing here, you can write a tabular column. So this is my tabular column having frequency, what is the magnitude, and what is the phase. What is the phase? So start from 10, make it 100, make it 500, make it 1k, make it 2k, make it 10k, make it 50k, make it 100k. You have the magnitude in dBs as minus 20 log of under root of 1 plus 2 pi f c r whole square. Phase is, this is phase is minus tan inverse of 2 pi f c r. So what is the value of r? R is equal to 1k, 1 kilo ohm, and c is equal to 1 microfarad. For different values of f, find magnitude phase, magnitude phase, magnitude phase, magnitude phase. Write the values and compare with this here. Can you see the comparison? Now you click on this, you click on this. Can you see for 1 kilohertz, what is the magnitude? It is minus 16.07 dBs. The phase is minus 80 degree. Suppose if you want to move this, you can move here. What is the frequency? Frequency is 300, and of course if you want to go for 100 hertz, you can just go for, okay, let me just go to this. I cannot edit there. Let me go here and set it at 100 hertz. I'm almost there at 100 hertz. You can see at 100 hertz what is the magnitude and what is the phase. Maybe at 1k you can find what is, maybe, of course I just set it as 500 hertz. This is at 500 hertz, what is the magnitude and phase. And at 1 kilohertz, what is the magnitude and phase. Maybe at 2 kilohertz, what is the magnitude and phase. Maybe at 10 kilohertz, what is the magnitude and phase. So this is how you can able to relate this magnitude and phase for a given frequency from the plot onto the readings that what you will be calculating, So, and of course we will come to the half power bandwidth. So what is this half power bandwidth? So half power bandwidth. So whenever the power is half, the corresponding voltage will become 1 over root 2 times, 1 over root 2 times. So 1 over root 2 times is actually, in terms of dBs, it corresponds to minus 3 dB, So what you can do is, to find out what is half power bandwidth, you can double click on this, get two cursors, place one of the cursor at the beginning and place the other cursor such that this magnitude difference is 3. So let me just change that, so that magnitude difference is 3. Can you see this is now 3? Just keep on moving that, so that this magnitude difference becomes minus 3. So now am I there at, yeah, I'm almost there at minus 3. Can you see this is minus 3, minus 3. So now what is the cutoff frequency? Of course, in this case for this circuit of RC network, 159 hertz happens to be the cutoff frequency. So now FC is 159 hertz. How to verify that this is the proper reading or not? So for that you can just come over here. What is this FC? So this will happen at a phase of minus 145 degree. Sorry, minus 45 degree, not minus 145, it is minus 45 degree. You can just go back and see at that frequency. Can you see at this frequency what is the phase? Phase is minus 45 degree. So you're going to have a phase of minus 45 degree at cutoff frequency. So let me just go back here and find out how it is 159. So cutoff frequency of this RC network is given by 1 over 2 pi RC. So this is 1 over 2 pi, R is 1K, C is 1 microfarad. If you find the ratio of this exactly comes out to be, that you can verify, 2 into pi into 1 exponential 3 into 1 exponential minus 6 equals, okay, now this is inverse. You can see it is 159.15 hertz, which is exactly what we found. So basically what I want to emphasize here is, whenever you are doing frequency response of a circuit, make sure that you are doing dot AC analysis, selecting a decade sweep, having sufficient number of points. Maybe let me just show you. Okay, suppose if the number of points are 5, how it looks like. If it is 5, of course for 5 it is almost looking the same. So let me just make sure that it is simply 1. Suppose if you have only 1, you can see this is how it looks. Can you see this is for every decade only? This is 1 point, this is second point, this is third point. Can you see this is looking not a smooth one? So to have a smooth one, you try to have as many number of points per decade. So even giving 100, okay, 1000, 10,000 will take lot of time. Just give considerably a nominal number can be 100. So 100 is will not take too much time, and it will be good in terms of its smoothness. And then most importantly, the frequency, sorry, this uh, source should be a voltage source, and this should be none, and you should be selecting a AC amplitude of 1. So this is a must for any frequency analysis. Assume that suppose by mistake if I select a sine, and if I don't specify this, and if I just give some amplitude of 1 volt, and what if I just give a frequency of something like 500 hertz, and then if I start running, suppose if I run, it says there is an error. What it is saying? No AC stimulus found. So since you are doing a AC analysis, but it is asking, okay, there is no AC stimulus found. So we have to come down here and then make that AC amplitude as 1. Suppose if I come down here and then make the AC amplitude as 1, so you can just run now. Now, even with this sign as 500, that will be overwritten by this. So that's why that is not considered here. Most importantly, you have to choose an AC amplitude of 1, and it's better that you have it as none. Suppose if you give it as 500, it will be in confusion. So what is this 500 and what is this one? So let us make sure that this is none and this is AC amplitude, so that you are perfectly aware that okay, you are having a source whose frequency is not specified here, but the frequency sweep is specified in your what the AC analysis. In the configuration you are setting that, and then of course you are doing the you're plotting the things, output, output itself will give the output of input, because input is 1, and you know how to know what is this magnitude and phase of the output response. So this is what is the frequency response. For this input frequency, sorry, current is not relevant here, so let me just delete that. Let me just take out this is what is relevant. The phase changes from 0 to minus 90 degree, so magnitudes keep going down, so to negative dB values. So thank you.